16th, two telescopes, one in Chile and another in South Korea, captured synchronized images of 3I Atlas that changed everything. The interstellar object had just entered a stable orbital corridor between Mars and Earth. That alone was rare. But what came next defied both models and expectations. Several highly collimated jets erupted from its nucleus. Not random outgassing, but structured, repeatable plumes. And this happened while the object was already under observation, leaving little room for speculation. No one predicted this behavior. No one understood it at first, and yet the data is clear. If you've been following this channel, you know 3I Atlas has never behaved like a typical comet. But today, we're not just talking about survival, we're talking about activation, something that may have been dormant until now. If you're as drawn to these mysteries as we are, like and subscribe. Drop a comment with your location and the time you're watching this, and let us know what you think this object really is, because after today, it might no longer be enough to call it a comet. At exactly 0412th Universal Time, something changed in the thermal signature of 3I Atlas. Until then, every reading from the Solar Terrestrial Imager Array had been within expected bounds. But in a 6-minute interval, 3 independent hotspots appeared on the surface, sudden, precise, and stable. One of the hotspots emerged in the night-facing region, entirely outside the reach of sunlight. A second was located at the rotational limb, where temperature gradients are usually soft and transitional. The third appeared near the southern axis, and remained locked in position even as the object rotated. Together, they formed a triangular pattern that rotated as a unit, but never shifted individually. The behavior did not match any known thermal process in natural comets. Each hotspot rose rapidly to a temperature of approximately 147 Kelvin. This is over 50 degrees warmer than the surrounding material. More importantly, all 3 reached their peak temperature within 90 seconds of each other and then held steady. For 4 hours and 18 minutes they remained constant. No decay, no fluctuation, no drifting. In known cometary physics, heat follows sunlight. Surfaces warm as they face the sun and cool as they rotate away. Sublimation occurs on the sunward side, venting gases that briefly increase the local temperature. But the hotspots on 3I Atlas did not follow this cycle. They ignored solar exposure. They remained fixed in geometry. And their decay curve, when it finally began, was synchronized to the second. The early hypothesis was internal pressure release. Perhaps the object had built up volatile gas chambers beneath an insulating crust, which then ruptured in sequence. But no pressure spikes were detected. No sudden bursts of mass ejection followed. Instead, what came next was even more unusual. Infrared telescopes from Earth, Mars orbit, and deep space all confirmed the same observation. Each hotspot was emitting a narrow cone of infrared radiation, not scattering heat, emitting it in a direction. The emission cones were measured at 5 degrees in width and displayed coherent pulsing at exactly 14.8-second intervals. This rhythm held across 3 instruments and 3 observation points. This was not noise. It was not background interference. It was structured. Thermal pulses in nature are chaotic. Lava fields radiate heat, but they do not pulse. Ice vents flicker, but not in lockstep. Radiation from decaying isotopes releases energy, but not in perfect cadence. These pulses were clean, timed, repeating. Not with data modulation or signal encoding, but with a stability that suggested regulation. At this point, astronomers stopped calling them heat zones. They began calling them emitters. A revised energy budget was drafted that evening. Based on thermal output alone, the total energy released by the 3 hotspots over a 4-hour window exceeded all predicted values by a factor of 8. That could only happen if the internal material was storing heat, or if it was converting energy into heat through an unknown mechanism. Either option was difficult to accept. But the data left little room for traditional explanations. No comet in recorded observation has ever emitted structured thermal radiation at stable frequencies from localized zones. No natural process explains directional mid-infrared emission from a rotating object in deep space. And yet, this is exactly what the data showed. This was no longer just a curious interstellar object. 3I Atlas had become thermally active, and that activation was not random, it was deliberate, or at the very least, governed by rules we do not yet understand. At 0447 Universal Time, just over 30 minutes after the thermal activation began, something unexpected erupted from the nucleus of 3I Atlas. A narrow, high-velocity plume shot out from the object's western quadrant, recorded in real time by the Japan Infrared Space Observatory. Its speed was measured at over 1,200 meters per second. It was sharp, structured, not diffused like typical cometary outgassing, but that was only the beginning. 18 seconds later, a second jet ignited from the opposite limb. 5 seconds after that, a third erupted from the trailing edge. All 3 jets stabilized within 30 seconds and began venting in perfect symmetry. They were spaced at exactly 120 degrees around the nucleus, not approximate, not organic, mathematically precise. The symmetry held across all observational frames. Multiple instruments confirmed that the 3 jets did not just erupt simultaneously. They operated as a system. Natural comet jets do not do this. Outgassing is typically irregular, driven by local pressure buildup, crustal weakness, or sunlight angle. Most comets vent from 1 or 2 active regions, which rotate in and out of solar exposure, creating intermittent bursts of gas and dust. Even the most active comets on record, like Hale-Bopp or 67P, showed chaotic venting behavior with no detectable symmetry. 3I Atlas violated every one of those expectations. Each of the 3 jets maintained collimated flow. That is, the plumes remained narrow, focused, and consistent in direction. Ground-based observatories in South America recorded spectral data that confirmed not only similar chemical composition across all 3 jets, but identical particle velocities. No turbulence, no cone spread. The density gradients were nearly identical, as if governed by the same internal pressure and nozzle structure. The term nozzle was first used hesitantly in internal reports, then became unavoidable. In engineering, a nozzle controls flow, focusing it, accelerating it, shaping its release into predictable geometry. These jets exhibited precisely those behaviors. They did not flare. They did not wander. They remained stable across a period of 12 full minutes. Then came the modulation. Spectral readings showed rhythmic variation in density every 6.4 seconds, a repeating pulse of lower and higher ion concentration moving down the center line of each jet. These modulations were synchronized across all 3 jets, despite the fact that they originated from different regions of the rotating body. The phase was identical. The alignment, perfect. This behavior has never been seen in any natural object. Researchers compared the pulse timing to known internal rotation rates and found no match. The object was not spinning quickly enough to create centrifugal venting on a 6-second rhythm, nor could internal geyser-like pockets release in such a clean pattern across separated zones. There was no physical connection between the jet regions, at least none visible on the surface, and yet the pattern persisted. By 5:01 Universal Time, the 3 jets began to slightly adjust direction. Not randomly, but together. Their angle relative to solar incidence shifted by 2 degrees over the next 5 minutes. It was enough to maintain the same outward trajectory in space despite the comet's slow axial rotation. This indicated not only that the jets were stabilizing the object, but that they were actively compensating for orbital drift. Multiple institutions submitted revised classifications that evening. The working label was no longer natural cometary jet. It became controlled directional emission. What had started as thermal anomalies was now becoming dynamic propulsion, and the symmetry of it all suggested something else entirely. This was not just venting. This was behavior, and behavior always implies a system. Roughly 1 hour after the first jets appeared, spectrometers around the globe began to report something unusual. These were not the emissions of ordinary cometary outgassing. The light, signature coming from 3I Atlas, contained lines that did not match what scientists typically expect from carbon dioxide or water vapor. Instead, the spectral fingerprints pointed to noble gases, specifically argon, neon, and xenon, in concentrations that broke the model instantly. The first red flag came from the European Southern Observatory. As its high-dispersion spectrograph locked onto the ion tail, it registered a pronounced presence of ionized argon-40. That alone was strange. But it was quickly followed by a sharper, deeper line. Xenon 129, then Xenon 136. These isotopes do not exist in meaningful abundance in natural comet tails. In fact, they are almost never observed outside of laboratory simulations or planetary atmospheres with deep geological histories. Neon emissions followed next. Their spectral peaks were blue-shifted, indicating a higher than expected ejection velocity. Yet the object itself was moving on a stable arc. There was no gravitational perturbation. The ions were moving fast, but only the ions. The solid body stayed steady. By 0530 Universal Time, 3 different observatories in Chile, Hawaii and Namibia had independently confirmed that the ion trail of 3I Atlas did not contain the standard water group radicals that typically dominate comet tails. The signature was off. No hydroxyl bands, no diatomic carbon. Instead, it was filled with monoatomic noble gases, which resist chemical bonding and are rarely expelled in large quantities. A new question formed in the research community. Were these materials being vented from the surface, or were they being generated by some kind of internal process? That distinction matters. Noble gases are often trapped in icy matrices, but for them to be released in this quantity, the internal composition of 3I Atlas would need to be unusually dense in volatiles, far denser than anything expected from an object that had spent millions of years in interstellar space. There is also the issue of decay chains. Xenon 129, for example, is the daughter product of iodine 129. The half-life is over 15 million years. If the xenon was recent, then something inside 3I Atlas had to be actively decaying, or generating it. Then came another anomaly. The James Webb Space Telescope focused its infrared suite on the inner tail and detected a compound previously unreported in any interstellar object. Trace signatures of nitric oxide and ammonia, both reactive, short-lived molecules, were present, yet the thermal environment suggested they should have broken apart long before detection. These molecules could not have been vented passively. They had to be shielded, encapsulated, or synthesized and released only moments before detection. This suggested a delivery mechanism, not random exposure. By the time the solar wind data from the Deep Space Climate Observatory came in, another layer of complexity was added. The ionized gases from 3I Atlas were not simply mixing into the solar stream, they were resisting it. The object's tail exhibited confinement. Ion trajectories were aligned rather than diffused. The plasma stayed focused. No scattering, no curling, just a long ribbon-like streamer of coherent energy stretching millions of kilometers behind it. This was not a cloud, it was a beam, and it was made of elements that should have been rare, scattered and disorganized, not concentrated and structured. Every model failed, every prior classification collapsed. At this point, it became impossible to explain the emissions of 3I Atlas using natural cometry processes. It was behaving as if it contained systems of storage, timing and release. Not chaos, control. At 0622 Universal Time, 3I Atlas moved into a precise orbital alignment behind Mars. For a brief window of 38 minutes, it passed through a partial planetary shadow. The effect was not a full eclipse, but rather a reduced solar flux, a soft, predictable cone of darkness cast by Mars onto the orbital plane. Astronomers anticipated this moment. It was a rare opportunity to observe the object's thermal behavior and outgassing patterns during a known dip in solar energy. The expected result was straightforward. Without direct solar radiation, surface temperatures should fall, active venting should decrease. Jets, if driven by sunlight, should weaken or shut down entirely. But what actually happened contradicted every one of those expectations. Within 3 minutes of entering the shadow cone, the infrared emission from 3I Atlas increased by 19%. Not decreased, increased. The 3 primary jets intensified, particle velocities rose, ion density along the beam vectors nearly doubled, and then, without warning, a 4th jet ignited. This new jet emerged from the southern polar quadrant. It had not been visible before. Its direction was downward, angled along the object's orbital path. It was weaker than the primary jets but highly collimated, structured, focused. Within 8 seconds it stabilized at a steady output and began pulsing with the same 6.4-second rhythm as the others. The question was immediate. How could outgassing increase when solar input dropped? One proposed answer was thermal inertia. Perhaps heat stored in the nucleus was being released with a time lag. But the timing was too precise. The thermal rise occurred only after the object entered shadow, and the 4th jet had never been active before. Something had changed in response to the eclipse itself. Spectral data added another layer. The composition of the 4th jet differed from the others. It contained higher ratios of carbon monoxide and nitrogen compounds. It burned colder. It burned cleaner. Its ion stream resisted solar wind deflection more than the others, and as the shadow deepened, its trajectory subtly adjusted. Not randomly, but toward the center of the cone. This behavior implied awareness, not consciousness, but alignment. A real-time reaction to a drop in solar energy, not by shutting down, but by compensating. The fourth jet appeared to function as a stabilizer or thruster, a counterbalance to the environmental change. Observers at the Indian Deep Space Station noted a secondary effect. The tail of 3I Atlas, already unusually narrow, began to curve, but not with the solar wind. It curved against it, adjusting toward the Mars-Earth axis. The curvature held for the duration of the eclipse, then slowly returned to baseline as the object re-entered full sunlight. This reaction was not passive, it was geometric. It maintained alignment with something outside the object itself, and the timing was exact, not gradual, not thermal, coordinated. Astronomers recalculated the object's energy budget using shadow-modified solar flux. The math no longer made sense. The amount of energy required to intensify the jets during eclipse exceeded what could have been stored inside the object, without overheating or fragmenting. There was no thermal lag large enough to explain the spike, and there was no precedent for activation because of shadow. This led to a new classification, reactive eclipse response, a category previously theoretical, never observed. The idea that a celestial object might behave differently in shadow than in light, not because of loss but because of threshold, was now on record. 3I Atlas had not gone quiet in darkness. It had adapted, and the eclipse became a test it passed, not with survival, but with precision. As the jets of 3I Atlas continued their structured emissions into the mid-morning hours of November 16th, thermal imagers began to report something even more perplexing than the surface-level heat anomalies. Beneath the surface, several meters into the nucleus, heat was building, not dissipating, not radiating outward, building. Using data from the Mars Infrared Orbital Surveyor and the Deep Sky Infrared Array, thermal penetration models were reconstructed to isolate the object's internal temperature distribution. What emerged was a heat map inconsistent with cometry structure. Instead of cooling from the outermost shell inward, 3I Atlas showed a reversed profile. Internal layers beneath the surface zones were retaining heat well above what should have been possible. The stable temperature gradient extended downward over 5 meters, with peak values maintained over a 4-hour observation window. This persistence raised serious doubts about any passive explanation. In known cometry models, volatile ices sublimate near the surface, driven by sunlight. As gas vents, internal material is exposed and cools as pressure is relieved. The cooling is rapid and predictable, but the data from 3I Atlas showed neither surface cooling nor internal collapse. Instead, the heat was contained and structured within concentric thermal zones. One hypothesis suggested a form of insulation, perhaps a regolith crust trapping energy. But further spectral analysis ruled this out. The crust was porous and fractured, not sealed. In fact, it appeared to encourage venting, not prevent it. Infrared emissivity measurements across the 3 primary hotspots showed no delay in radiative loss. The surface was emitting freely, and yet heat just below that surface remained stable. That observation alone changed the nature of the investigation. Stable subsurface heat implies one of 3 things. Either the internal structure is absorbing energy from a non-solar source, or the energy is being distributed through an unknown transfer mechanism, or, most controversially, the internal system is managing its own heat intentionally. The second possibility gained traction among thermal physicists. They proposed a model based on radiative feedback loops. In this model, trapped gases within narrow channels circulate heat in a manner similar to terrestrial thermal pipes. However, for such a system to work, it would require complex internal geometry, chambers, tunnels, and directional flow pathways, none of which had ever been observed in natural small bodies. An alternate group proposed an even more radical explanation, that internal chemical reactions were responsible, in particular, exothermic recombination of dissociated molecular gases, triggered not by sunlight, but by pressure gradients or magnetic fields. This would suggest that parts of the object's core are chemically active, not inert frozen ice, but reactive zones capable of timed energy release. The final clue came when the James Webb Space Telescope conducted high-resolution imaging of the nucleus in the near-infrared spectrum. It detected low-frequency thermal pulses emerging from beneath one of the active jets. These pulses were regular and synchronized with surface activity. More importantly, they repeated with an echo pattern, not as a decaying wave, but as a reverberation consistent with structured geometry. This reverberation implies containment, not just shape, function. A body that can trap heat and release it in pulses is not simply responding to solar energy, it is managing energy. By 7/10 universal time, the 3 original hotspots had maintained their thermal output for nearly 3 full hours. Internal temperatures had dropped by less than 1 Kelvin. That level of stability has never been recorded in any known comet. 3I Atlas was not cooling as it should have. It was holding heat. And holding heat suggests something crucial in physics. It suggests intention, or at the very least, capacity. At Joe 713 Universal Time, observers at the Pan-Equatorial Surveillance Network began to notice a subtle but critical shift. The 3 main jets erupting from the surface of 3I Atlas, previously locked in symmetrical fixed positions, were beginning to move, not in response to thermal turbulence, not due to rotation or solar wind distortion. The jets were realigning. Over the span of 20 minutes, each jet vector rotated between 4 and 7 degrees relative to its previous orientation. These movements were not random. Each jet adjusted in synchrony with the others, preserving the 120-degree separation that had defined their original symmetry. The plume angles evolved as a unit, as if the system was executing a coordinated maneuver. This was not typical behavior for cometary jets. In every known natural case, comet jets are fixed to specific surface locations. They emerge from fractures, pockets of volatile ice, or weak spots exposed to sunlight. As the comet rotates, those jets appear to move, but their vectors are determined entirely by surface geography and passive physics. They do not reorient themselves independently. But here, the jets of 3I Atlas were detaching from surface-fixed angles. They began curving toward a new trajectory, one aligned with the solar vector at a slightly modified incidence. As the nucleus continued its slow axial rotation, the jets maintained their realigned orientation rather than remaining tied to the rotating surface. In effect, they decoupled from the spin and held position. Spectrographic imaging from the Lunar Polar Array confirmed this change with remarkable precision. The new jet vectors converged toward a common solar relative axis, offset by 5 degrees from the orbital tangent. This angle shift allowed the object to maintain a net acceleration vector aligned with its new velocity path, a form of directional stabilization. This suggested the jets were not simply reactions to internal pressure, they were being steered. Additional data came from Doppler velocity measurements of the jet particles. As the vector angles shifted, the velocity profiles changed proportionally. The leading edge of each jet accelerated while the trailing edge decelerated, effectively bending the plume without increasing overall thrust. This curvature in flow dynamics has only ever been seen in engineered systems, such as ion engines or plasma deflectors. There was more. Embedded within the ion stream of each jet, magnetohydrodynamic sensors detected faint but coherent wave patterns. These waves, travelling along the direction of flow, exhibited phase locking across all 3 jets. The waves pulsed at 8-second intervals, with phase offsets that preserved geometric balance. No natural process is known to maintain such sustained synchronicity under varying thermal and gravitational conditions. By 0734 Universal Time, the jet vector shift had stabilized. All 3 jets held their new positions relative to solar incidence and orbital velocity. The net effect was a steady adjustment in the object's acceleration vector, a micro-correction to its trajectory without altering its overall speed. This was a controlled change in orientation. It was not violent, it was not chaotic, it was targeted and stable. Astrodynamics teams from multiple institutions began modelling the implications of this shift. If 3I Atlas is capable of altering jet vectors in response to positional geometry, then it possesses at minimum a feedback system, one capable of sensing position, calculating orientation, and adjusting flow accordingly. Whether this mechanism is natural, chemical, or something more advanced remains unknown, but the function is clear. jet vector control allows course correction. Course correction implies path prediction, and a predicted path implies purpose. At 0742 Universal Time, a team from the Mauna Kea Observatory in Hawaii initiated a spectral contrast analysis to measure light behavior around 3I Atlas. Their goal was simple: determine how much of the light observed from the object was reflected sunlight versus how much was self-emitted radiation. In natural bodies like comets or asteroids, the reflected to emitted ratio is well understood. The surface reflects incident solar radiation based on its albedo, while the warmer regions emit infrared radiation in predictable thermal bands. Most comets have low albedo values, meaning they absorb most of the sunlight and emit weak thermal signatures. The balance tilts heavily toward reflected light at visible wavelengths and emitted radiation in the infrared. But 3I Atlas did not behave like other comets. The first indication came from polarization measurements. Normally, reflected sunlight becomes polarized as it bounces off the surface of a rough object. Polarimetric sensors on Earth and in Mars orbit found that the light near the active jets was not polarized in a way consistent with reflection. In fact, the polarization pattern was inverted, stronger at angles where it should have been weakest and absent in areas where it should have peaked. That pointed toward a dominant emission source, rather than reflected sunlight. Then came the spectral ratio measurements. When sunlight reflects off a dusty surface, the spectral signature closely matches that of the solar spectrum with minor reddening from the surface material. But the light from the jet regions of 3I Atlas showed no such correlation. The visible and near-infrared wavelengths were broadened and shifted toward higher intensities. The emission spectrum contained active bands of excited molecules not commonly seen in surface reflection. Most striking was the presence of a sharp spike in the mid-infrared range centered around 12 micrometers. This spike was not solar in origin, it was thermal radiation, emitted from the jet regions themselves. Its intensity varied on a rhythm identical to the jet pulses observed earlier, a synchronized modulation of brightness that matched the 6.4-second cycle. In other words, 3I Atlas was not just reflecting sunlight, it was emitting radiation, and that emission was timed. By 08 Universal Time, the team compared emissions from three angles. One measured the sunlit hemisphere, the second focused on the shadowed hemisphere, the third monitored the area between the three jet origins. If emission was caused purely by solar heating, the night side should have been dark. Instead, it glowed, not dimly, actively. The radiation curve remained stable, suggesting that the energy source was internal, not surface reflected. To cross-check the data, readings from the James Webb Space Telescope were brought into the analysis. Webb's near-infrared spectrometer showed consistency with active emission, rather than passive reflection. The same spectral curves appeared regardless of solar angle. The object's emission remained constant even as it moved through orbital positions that would have dramatically changed reflectivity in a passive system. The implication was clear. This object was not shining because the sun lit it. It was shining because it was generating light. That subtle but critical distinction has enormous meaning in space physics. Passive reflection is incidental. It reveals surface properties and orbit orientation. Active emission suggests ongoing processes. It means that something inside the object is producing energy, either through thermal storage, chemical reactions, or controlled output. For 3I Atlas, that control appeared structured. The brightness rose and fell in rhythm. The emission stayed stable through eclipse and re-entry, and the jets radiated not just particles, but photons in a deliberate direction. This was not a dusty snowball scattering sunlight into space. This was an emitter. And in physics, emission tells us more than reflection ever can. It tells us something is working, something is alive in the system, and something is choosing to shine. By 0814 Universal Time, a consistent pattern had begun to emerge in the data streams from multiple observatories. The jets erupting from 3I Atlas were not simply continuous streams of gas and dust. They were modulated. Each of the three primary jets displayed rhythmic pulses in both light output and ion density. What made this remarkable was not just that the pulses existed, it was that they were synchronized. All three jets emitted a measurable increase in brightness and particle velocity every 6.4 seconds. This cycle repeated precisely across instruments in Hawaii, Chile, Namibia, and orbital platforms above Earth and Mars. Each pulse rose in intensity over the course of 1 second, then returned to baseline over the next 5. The shape of the pulse curve was consistent. The timing did not drift. No jitter was detected. This level of stability suggested something more than natural pressure release or chaotic internal geysers. In natural cometary systems, outgassing events are driven by thermal gradients. When heat penetrates porous subsurface layers, pressure builds up until the crust fractures or vents. The resulting outflow is irregular and varies with sunlight, composition, and rotation. There is no known mechanism in nature that produces perfectly timed bursts across spatially separated jets with stable intervals and no decay. Yet 3i Atlas was doing exactly that. To test the consistency, the European Space Agency cross-checked signals from their orbital infrared sensors with optical pulses observed from the ground. The result confirmed pulse lock. The emissions were not only synchronized in time but also phase-matched. That means each jet increased and decreased output in unison, regardless of their physical location on the nucleus. Even more intriguing, the jets maintained this synchronization through rotational movement. As the object turned, the pulse timing did not shift. This behavior suggests a global internal clock or regulator, some organizing mechanism capable of coordinating multiple emission points with high precision. Thermal feedback loops cannot explain this, nor can rotational harmonics. The rotation period of 3i Atlas is too slow to create such high-frequency cycles. Its internal structure is likely too small and cold to support electrical oscillations that could drive such regularity passively. The pulses were not limited to light or gas flow. They also extended into the ion trails. Spectral readings from the tail revealed periodic increases in ion concentration and charge separation that matched the surface pulses. Every 6.4 seconds, the density of doubly ionized neon and argon rose, peaked, and faded in step with the jets. The tail was not a static trail of particles. It was a dynamic conveyor of pulses, a transmission system. What stood out further was that the amplitude of the pulses adjusted slightly depending on the object's orbital vector. When 3i Atlas reached the midpoint of its shadow crossing behind Mars, the amplitude increased by 12% across all readings, not gradually, instantly. The change occurred at the exact moment the object entered full shadow. This implied real-time environmental response. A spacecraft or engineered probe might use pulsed thrust for stabilization, signaling, or energy regulation. In human technology, pulse-locked systems are used to maintain balance and precision in satellites and orbital instruments. Nature does not typically produce this behavior without a trigger, and yet here was an interstellar object doing just that, emitting symmetrical, timed pulses of energy and material into space as it rotated freely, unaffected by outside forces. The question was no longer if 3i Atlas was active. The question was whether the timing we observed was the result of design. Because in science, when 3 emission points pulse together with no decay, no drift, and no trigger except orbital position, it is no longer simply a jet. It is a signal, and signals require mechanisms. At 8:32 Universal Time, a cascade of unexpected readings began flowing in from magnetometers aboard the Martian orbital platform MSAT-2. These instruments, originally intended to map residual crustal magnetism on Mars, detected an anomalous fluctuation in the surrounding plasma environment. The origin was not solar, nor was it geological. The signal was traced back to a point roughly 60,000 kilometers beyond the planet's orbital shadow. It came from the direction of 3i Atlas. The disturbance was weak but coherent, a patterned oscillation in the local magnetic field repeating every 6.4 seconds, the same interval as the jet pulse emissions recorded earlier. The magnetic wave was low amplitude but extended. It propagated across a radius of over 7,000 kilometers, with field distortion strongest along the solar-wind interface. Magnetosphere interference of this kind is not typical for small bodies. Comets and asteroids are not magnetic. They do not generate their own fields. Occasionally they exhibit magnetic moments due to trapped solar particles, but these are weak and chaotic. They certainly do not modulate surrounding space in timed intervals. But 3i Atlas was doing exactly that. Earth-based monitoring systems joined the observation effort. The Global Magnetospheric Sensor Array reported correlated fluctuations in near-Earth space, especially within the Lagrange point corridors. These distant echoes matched the Martian signal, both in frequency and shape. The interference was pulsed, not sustained. It had a beginning, a middle, and an end, and it followed the emission cycles of the jets. The idea that 3I Atlas might be interacting with the solar magnetic field directly was not immediately accepted, but over the next 40 minutes, additional spacecraft confirmed the disturbance. The Parker Solar Probe, though millions of kilometers away, registered small harmonics in the heliospheric current sheet, aligned again with the same 6.4-second window. The object was not just ejecting matter, it was coupling into the electromagnetic fabric of the solar system. There was one more detail. The direction of the interference was not random. The magnetosphere modulation exhibited directional bias, favouring one vector more than others. That vector pointed not away from the Sun, but at an oblique angle, roughly 28 degrees off the solar axis, in the same general direction as Earth's orbit. The signals pulsed outward along this path, creating a corridor of minor distortion, extending tens of thousands of kilometers wide. What could cause this one hypothesis involved ion cyclotron resonance, a process where charged particles in plasma environments spiral around magnetic field lines and emit waves. This is a known phenomenon near planets and in comet-solar wind interactions. But in every prior case, the effect was chaotic, localized, and heavily dependent on solar particle density. With 3I Atlas, the modulation was structured, timed, and persistent even during periods of low solar wind pressure. It appeared to function as a transmitter, a field-modulating envelope, synchronizing emission with motion. Researchers at the Max Planck Institute proposed a new term for the phenomenon, directed field bloom, a hybrid between electromagnetic wake and modulated pulse wave. In this model, 3I Atlas was not just being acted upon by space, it was shaping its own magnetic interaction zone through controlled outflow and pulsed emissions. This would require not only ionization at the point of emission, but coordinated charge separation and directional vectoring, none of which are present in traditional comets. The object was behaving more like a field emitter or plasma sail than a frozen interstellar body. By 0857 Universal Time, consensus formed around one core fact. 3I Atlas was affecting the solar magnetic environment in real time, and anything that modifies the magnetic medium of space, with rhythm, direction, and timing, is no longer passive. It becomes part of the system, an actor, not an object. At 0906 Universal Time, as 3I Atlas continued its orbit just beyond the night side of Mars, a new signal emerged. It did not come from the object itself, it came from Mars. More precisely, from reflected spectral lines captured by a coordinated planetary observation system operating from orbit and from the Martian surface. The European Space Agency's Orbital Surface Reflectance Array, stationed above Mars's southern hemisphere, began detecting anomalous spectral lines in light that had first passed through the emission trails of 3I Atlas and then bounced off the upper Martian atmosphere. This indirect method, reading a signal not from its source, but from its echo, provided an entirely different lens on the object's chemical behavior. What the team found changed the nature of the investigation. In the returning spectra, narrowband lines were detected in the ultraviolet and near-infrared ranges. These lines did not correspond to known atmospheric interactions or surface reflections. They were not native to Mars, nor were they common in the interplanetary medium. Instead, they matched lines produced by highly excited molecules, including diatomic nitrogen in Rydberg states and ionized sulfur chains, which require precise energy conditions to form. These were not thermal emissions, they were interaction residues. This meant that the gases or particles emitted by 3I Atlas were not just dissipating into space, they were interacting with Mars's upper atmosphere in a structured way, energizing, reflecting, and leaving behind a repeatable signature. By 0914, the Chinese Tianwen-1 orbiter confirmed the same echo patterns, independently capturing a mirrored set of spectral lines on the opposite hemisphere. This symmetry indicated that the signal was not localized or the result of equipment interference. It was planetary-wide, diffuse but coherent, and traceable to a precise orbital corridor, the wake path of 3I Atlas. Further analysis revealed modulation. The echo signals were not constant. They peaked every 6.4 seconds. precisely matching the pulse timing of the jets. Even at this indirect distance, even through atmospheric scattering and surface deflection, the timing survived. It was intact. This proved the emissions from 3I Atlas were not only directed, but persistent enough to imprint on another celestial body. And that body was responding. Martian atmospheric density at high altitudes is thin but not null. When charged particles pass through at sufficient velocity, they induce chemiluminescence, light produced by chemical excitation. This phenomenon, usually weak and irregular, appeared amplified during the passage of 3I Atlas. Photometric sensors on the surface, originally designed to monitor auroras and dust storms, picked up repeating flashes in the upper sky. These flashes were synchronized with the object's jet pulses, always 6.4 seconds apart. They appeared as brief violet and green flickers, faint but detectable in both hemispheres. The Martian sky was pulsing in reply. The implications ran deep. If emissions from an interstellar object can leave behind timed chemical traces in the atmosphere of a planet it never touches, then that object is not inert. It is projecting energy across space in a sustained, organized pattern. The emissions were not random, nor were they directional accidents. They were structured pulses with the capacity to echo, not just in light, but in chemistry. Echoes suggest repeatability. Repeatability suggests predictability. And predictability in astrophysics often implies intent, or at least functional purpose. Mars had become a mirror, not just to sunlight but to something more precise. It reflected an interstellar pattern back toward Earth, where instruments detected not just light, but information. A repeatable, structured imprint of an object that was supposed to be passive. But now, in its own reflected voice, 3I Atlas had spoken, and the planet next door had answered. At 0922, universal time, orbital tracking systems detected something that should not have been possible. The object known as 3I Atlas had entered a segment of orbital space where multiple gravitational influences intersect, including Mars, the Sun, and several minor bodies along the same plane. In this region, slight instabilities in motion are expected. A comet or asteroid passing through would typically exhibit minor deviations, either accelerating under solar pull or shifting trajectory from gravitational assists. But 3I Atlas did not deviate. It held position. Not in absolute terms, it continued forward along its general orbit, but in vector and angular velocity. Over a 12-minute observation window, the object's path showed no measurable change. No tilt, no yaw, no perturbation. Its forward momentum remained constant to within 1 part in 10 million. For a natural body passing through a gravitationally complex corridor, this degree of trajectory rigidity is virtually unheard of. The Deep Space Navigation Array confirmed the reading, using Doppler shift measurements and long baseline. Interferometry, the system calculated real-time velocity changes across 5 observation points. The result showed a flat acceleration curve, 0 deviation across all axes. It was as if the object had locked its course. This led to a new round of orbital modelling. Physicists from the Celestial Dynamics Research Group ran simulations based on current gravitational maps and object mass estimates. In every plausible scenario, 3I Atlas should have experienced minor drift. Mars alone exerts enough pull at this range to induce a measurable shift in heading. Solar pressure, magnetic deflection, and even particle drag from the thin interplanetary medium should have contributed to cumulative error. Yet no correction was necessary, because no error had occurred. This phenomenon was labelled the trajectory hold, a condition in which the object's course remained unaffected by environmental forces within a specific time frame. The only known explanation for this in artificial systems is the use of active stabilization. Satellites and deep space probes maintain such holds using microthrusters, gyroscopes, or reaction wheels. These systems detect minute shifts and compensate instantly to maintain heading. There is no evidence of such systems on 3I Atlas, but the effect was present. The jets emitted from the object, synchronized and pulsed, may offer a partial explanation. If they functioned as attitude stabilizers, even with minimal thrust, they could in theory counteract small vector deviations. However, this would require a feedback mechanism, one capable of detecting position and responding with precision. It would also require constant timing and symmetrical force distribution. That is exactly what had been observed. The pulse cycle remained locked at 6.4 seconds. The jet orientations remained fixed relative to solar geometry, and the trajectory remained flat. If the jets were compensating, they were doing so in real time, with no visible delay or oscillation. By 0935 universal time, the object exited the gravitational corridor and entered a more stable heliocentric path. Still, no drift occurred. Tracking systems across Earth, Mars, and lunar bases confirmed absolute path retention to within sub-millimeter resolution. This kind of stability cannot be coincidental. In orbital mechanics, natural bodies wander. They respond to chaos. Only engineered systems hold. A trajectory hold, then, is not just an observational term. It is a statement. It implies that the object knows where it is, and that it has chosen not to move. By 9.46 universal time, after nearly 5 hours of continuous observation, researchers noticed something that upended the foundational assumptions about 3I Atlas. The jets were still active. The pulses continued with mechanical precision. The emissions remained focused and symmetrical. But the nucleus of the object, the body itself, showed no corresponding spin. It was not rotating. This defied the basics, principles of Newtonian physics applied to outgassing. In comets, outgassing produces torque. As volatile materials heat up and escape, the force of the release exerts pressure on the body, often resulting in spin acceleration or, at minimum, rotational drift. Even weak jets can create measurable torque over time. Asymmetric outflows should twist the object gradually, and when multiple jets are active, they typically act as thrusters, pushing, tilting, spinning. Yet 3I Atlas remained stable. Radar reflections from the Lunar Polar Radar Station confirmed the data. Surface albedo patterns remained fixed over time. No rotation markers shifted. The same points on the object's surface remained in view through each full hour of imaging. This was not slow rotation. It was rotational lock. The object had entered a state of outgassing without spin. To confirm this, Doppler shift measurements were taken from opposing hemispheres of the object. If any rotation existed, even slight, a measurable shift in spectral lines would appear due to relative velocity on the advancing and receding edges. But there was none. The readings were flat. No edge moved faster than the center. No indication of spin. This behavior is virtually unknown in natural bodies. One explanation could be internal mass symmetry. If the object's center of mass and outgassing sources are perfectly balanced, the net torque could cancel out, but the symmetry required for this would be near perfect. Natural comet nuclei are jagged, irregular, and chaotic. Their vents open unpredictably. No known interstellar object has ever displayed such stability under sustained outflow. Another hypothesis involved rotational damping. Perhaps 3I Atlas once rotated but has since been slowed to a halt by environmental friction, solar wind, electromagnetic braking, or tidal effects. Yet modelling shows this is unlikely. The timescales for such damping far exceed the current mission timeline. The object would have to be actively resisting spin as forces attempt to initiate it. That would require some form of stabilization, and the only mechanism observed that could serve this purpose is the trio of jets themselves. If the jets were not just releasing pressure, but responding to microforces in real time, adjusting their vector outputs in synchronized opposition, then they could in theory create a net zero torque system. In simpler terms, they would be functioning as controlled thrusters, actively balancing the object in place. This implies feedback, it implies sensors, it implies intention. By 10:01 universal time, the object had maintained jet activity for over 5 full hours without any measurable spin. The pulses continued to fire at regular intervals. The orientation of the jets remained locked, and the body of the object, against all expectations, stayed still. This is not how comets behave. This is not how dust balls from deep space respond to energy. This is behavior consistent with stabilization. And stabilization, in any engineered system, is never accidental. It is a choice, a method, a way of saying the object is not just ejecting material to survive the sun's heat, it is holding position. Because something, somewhere, needs it to remain exactly where it is. At 10:12 universal time, the high-orbit infrared observatory above Earth initiated a full-spectrum scan of 3I Atlas. The objective was to monitor surface temperature, internal heat signatures, and fluctuations in emitted thermal radiation. The scan was timed to coincide with the pulse window of the active jets. What the observatory detected was not just heat, it was modulation. Infrared cameras recorded a repeating pattern of flickers across the object's surface. These flickers were not due to sunlight. The object was in partial shadow relative to the sun during this window, and the radiative profile showed emission rather than reflection. More importantly, the pattern was pulsed, not random, not chaotic. The infrared signature brightened and dimmed every 6.4 seconds, perfectly in phase with the jet emissions. This rhythmic thermal fluctuation spanned a narrow band between 8 and 14 micrometers, a range typically associated with warm dust or active mineral reactions. But the brightness of the pulses did not fade with time, it remained constant. Each flicker was identical in intensity and timing. This ruled out surface cooling or rotation effects. The object was not turning to reveal hot and cold sides. It was stationary and pulsing from within. To verify the data, the lunar thermal grid aimed its ground-facing sensors at the same target window. The Moon's position allowed for simultaneous observation from a different angle. The results matched. The same 6.4-second pulse appeared. Identical flicker intervals, identical intensity changes, different angle, same result. This ruled out instrumental error. The infrared flicker was real, and it was global. Each time a jet activated, the surrounding surface emitted a slight spike in infrared radiation. This was not due to jet heat alone. The jets originated from fixed points, but the thermal pulse echoed across the body of the object, like a wave expanding through solid material. That implies internal coupling. The jet pulses triggered an object-wide thermal response. In natural systems, this type of behavior would require a highly conductive internal structure, a material that could absorb and re-emit heat nearly instantaneously. But cometary cores are made of porous ices, organic dust, and fractured rock. They are insulators. They do not transmit heat quickly. The only bodies known to respond to internal stimuli with whole-body thermal pulses are engineered composites: spacecraft hulls, reactor surfaces, artificial shells. Moreover, the flicker pattern included localized hotspots that did not match any known outgassing site. These hotspots appeared just milliseconds before the jet pulses, suggesting a chain of events. First, a rise in thermal energy across specific zones, then a centralized pulse, then jet ignition. The sequence implied a pre-programmed cycle. By 1027 Universal Time, researchers overlaid the thermal pulse data with previous brightness curves in the visible spectrum. The alignment was perfect. The object flickered in infrared, and then, milliseconds later, in visible light, a staggered signature that has only been observed in synchronized emission systems. These patterns are common in artificial satellites when thermal regulators adjust internal heat and radiative surfaces respond. No natural comet has ever exhibited this. One possible explanation offered was electrothermal coupling, where internal capacitive structures build charge and release energy in pulses, creating brief localized heating. This would explain the cycle regularity in the pre-pulse warm-up zones, but it would also require circuitry, and structure, and purpose. The data was submitted to the Interplanetary Thermal Analysis Network for peer confirmation. Their conclusion was unanimous. 3i Atlas does not radiate heat the way natural bodies do. It flickers, with timing, with symmetry, with intent. In deep space, heat is not just a byproduct, it is a signature, and 3i Atlas just signed its name. At 10:41 Universal Time, surface imaging teams monitoring 3i Atlas from the ESA's high-fidelity imaging platform noticed a subtle but consistent behavior. Small fragments were being ejected from the object's surface, not in explosive bursts, not in chaotic sprays, but in a pattern. Every few minutes, a group of particles would detach from specific zones. These zones were not chosen at random. They were aligned with the object's emission poles. This behavior was catalogued as non-random surface shedding. In typical cometary systems, surface shedding occurs due to thermal stress. Sunlight heats up volatile ices beneath the crust, building pressure until the surface ruptures. This produces sudden and uneven bursts of material from weak points across the body. The process is messy, spontaneous, and location agnostic. But 3i Atlas was doing the opposite. The shedding happened in geometric alignment. Sensors on board the Martian orbital imager captured a wide-angle time-lapse showing over a dozen surface shedding events. Every event emerged from one of three fixed surface regions, one near the equatorial jet origin, one along a lateral vent, and one at the trailing hemisphere. Each ejection followed a regular spacing interval of approximately 180 seconds. The fragments released were uniform in size. Spectral analysis from the reflected light off the particles showed consistent composition, high carbonaceous content with traces of crystalline silicates. No variation in composition between ejections was detected. This ruled out random crust rupture. The material was not chaotic debris, it was consistent ejecta, and the velocity of ejection was low. Each fragment left the surface at a relative speed of less than 2 meters per second, too slow to be caused by pressure buildup alone. These were not being blasted away, they were being released, almost placed into drift. Orbital simulations predicted that the ejected fragments would remain loosely in formation behind 3I Atlas, trailing it in a curved arc. Within minutes, this prediction was confirmed. Instruments tracked the newly formed particle field. It did not disperse chaotically. Instead, the particles fell into a staggered array, distributed along 3 symmetrical arcs, each aligned with the jet vectors. This was not how natural shedding works. It resembled a deployment pattern. Even more curious was the timing. The surface shedding events did not occur at random intervals. They aligned with the internal 6.4-second pulse rhythm. Not with every pulse, but at a precise harmonic, every 28th pulse cycle. This exact ratio suggested an internal trigger, something counting cycles, something deciding when to release. Further examination of the surface imaging showed that the shedding zones darkened slightly before ejection. Not from shadow, but from thermal drop. Infrared sensors recorded brief temperature declines in the shedding regions just prior to release. This suggested a cooling mechanism, perhaps a sealing action, immediately before material separation. In engineered systems, such behavior can prevent unwanted thermal spread or structural stress. Natural comet crusts do not do this. There are no known examples of bodies shedding surface fragments in timed, spaced intervals with uniform mass and structure, and then forming symmetrical debris fields in orbit. By 1059 Universal Time, all 12 surface shedding events had been recorded, logged, and tracked. The resulting fragments remained visible for several minutes before dispersing along the object's wake. Some researchers proposed passive surface delamination, a natural peeling effect due to differential heating. But this explanation fails to account for the timing, the regular spacing, the repeated zones, and the orbital symmetry. This was not delamination, it was procedure, controlled loss, a scheduled discard. And in physics, when an object sheds material at predictable intervals, at fixed locations with consistent mass, it is no longer crumbling, it is operating. At exactly 11:06 Universal Time, during a continuous multi-angle observation window, analysts monitoring the 3 synchronized jets on 3I Atlas noticed something subtle but persistent. The jets were not firing at the same absolute moment. There was a microsecond delay between each. The emissions were still pulsing every 6.4 seconds, as recorded earlier, but the start of each jet's pulse occurred slightly offset from the others, in a precise and consistent sequence. This became known as the jet lag delay, index. The leading jet, aligned closest to solar azimuth, ignited first. Exactly 212 milliseconds later, the second jet flared. The third followed at 420 milliseconds after the first. This triangular lag pattern repeated across all pulse cycles. It never shifted, it never reversed. It held true regardless of the object's rotational position, which by now had already been confirmed to be locked. The implications were immediate. In natural comet systems, multi-jet behavior is driven by heat and pressure, acting on different surface zones. While activation timing can sometimes appear offset due to irregular vent geometry, it is chaotic and variable. No known natural object produces this level of synchronization with such a consistent delay structure across thousands of cycles. To rule out observational error, a cross-instrument verification was conducted. The Near-Mars Spectral Radiometer, the Earth-Sun Lagrange Station Infrared Array, and the Lunar Observing Dome all recorded the same pulse offsets. Data latency was compensated. Optical corrections were applied. The delay was real, but it was not just delay, it was signal structure. The delay values between jets were multiples of 106 milliseconds, suggesting a system based on the internal clock cycles. This would be unusual in a thermodynamic body, extremely unusual, but completely logical in artificial systems. Communication protocols, timing pulses, and signal relays often operate on harmonic intervals. The pattern here was unmistakable. One base unit repeated with precision. The object was not simply pulsing 3 jets, it was cascading them. The delay index further revealed directionality. Each delay introduced not just a pause, but a slight angular difference in the direction of force output. As one jet fired and finished, the next initiated at a slightly different axis, creating a ripple effect in the total vector push. This ripple was not random. It created a spiral offset in the plasma exhaust, visible in long exposure imagery. That spiral matched the orbital vector of 3I Atlas. In artificial propulsion systems, staggered jet ignition is used to minimize torque while maintaining thrust. It allows for stabilization while avoiding overcorrection. Satellites and spacecraft use similar phased firing in cold gas or ion thrusters to maintain heading without introducing unwanted spin. So the object was not just stabilizing its path, it was smoothing it. Maintaining control without rotation, using delayed thrust to match orbital demands, and doing so across 3 independent jets without any detectable error over hundreds of cycles. One more detail emerged. The delay index began to slightly compress during moments of external interference. When the object passed through a minor solar wind shear, recorded by the heliospheric monitoring network, the delays tightened by 8 milliseconds. This change occurred simultaneously across all sensors. The delay compression suggested real-time adjustment, a form of environmental compensation. Not only was the object cascading its jet emissions with mechanical timing, it was adapting those timings to match surrounding solar activity. That behavior does not emerge from ice and dust, it emerges from programming. A jet lag delay index is not just a measurement, it is a signature of intention. Because in orbital dynamics, only 2 kinds of objects modulate force in real time: satellites and systems designed to behave like them. At 11:22 Universal Time, deep space gravimetric sensors began registering a subtle shift in the orbital corridor near Mars's Lagrange point 2. This region, a gravitational balance zone trailing the planet, is commonly used by satellites to maintain low-energy orbits with minimal fuel expenditure. Under normal conditions, the space near Lagrange 2 is quiet. Dust particles drift slowly. Radiative forces balance against gravity. But on this morning, something was moving differently. The drift patterns of background particles began to change. The alteration was first noticed by the Lagrange Path Mapping Array, a passive monitoring grid designed to track the trajectories of microparticles and magnetic interference fields. The system logged a new directional bias forming across the drift field. Dust that would ordinarily float in low-energy spirals began arcing toward a new vector, one that aligned not with the Sun or Mars, but with the orbital wake of 3I Atlas. The data showed a slow but measurable migration of mass. This phenomenon became known as the Lagrange drift interaction. It was not gravity-driven. 3I Atlas did not possess enough mass to alter the path of these particles through conventional gravitational pull, and yet the motion was real. It occurred consistently across a 5,000-kilometer radius centered behind the object's position. Spectral analysis of the drifting particles revealed something stranger. They were being electrostatically sorted. Fine grains with high surface charge began moving earlier than their neutral or denser counterparts. The lighter particles exhibited velocity increases inconsistent with solar wind exposure. The directional bias held steady, showing a field influence that did not originate from the Sun. Instead, it pointed back to the pulsed emissions of 3I Atlas. This meant that the jets, or some secondary process linked to them, were generating a moving field envelope strong enough to influence charged particles even after initial exhaust had dispersed. The emissions appeared to extend far beyond the object's body, forming what researchers began calling a drift corridor. This corridor was narrow, roughly elliptical in cross-section, and maintained directional coherence for over 12,000 kilometers behind the object. Within this space, particles experienced subtle reorientation, accelerating toward the object's vector path and then slowing, once they reached its outer boundary. The pattern was repeatable. It was not turbulence, it was a channel. Natural comets do not do this. Outgassing in typical cometary behavior results in chaotic dispersion. Particle clouds diffuse in all directions, especially under solar radiation pressure. But 3i Atlas was producing linear particle flow, directional and persistent. At 11:38 Universal Time, the Mars Sunline sensor registered a secondary interaction. A trailing cloud of ions, originally ejected over 90 minutes earlier, crossed into the Lagrange corridor and experienced minor compression. Instead of dispersing, the ions decelerated and clustered, briefly forming a narrow band aligned with the primary orbital vector. This compression suggested a field-based influence stronger than solar drag. Researchers proposed that the object might be leaving behind a low-frequency electromagnetic path, one capable of momentarily capturing and slowing material in its wake. Such phenomena have been observed only in tethered satellite systems and magnetic sail experiments. Here, it was coming from a comet, or what was once believed to be a comet. The drift interaction concluded by 11:44 Universal Time, but the altered particle vectors persisted. Even after the objects moved further along its orbit, the corridor remained visible in high contrast imaging, like the faint wake of a ship in calm water. Except this ship was gliding through gravity and leaving trails in the dust. Lagrange drift interaction is not a natural feature of interstellar bodies. It is a process, and process implies function. Because when an object pulls particles into alignment without touching them, and when those particles follow a hidden corridor through space, that object is no longer just passing through, it is guiding. At 11:49 Universal Time, during a coordinated deep scan across multiple frequency bands, observers detected a recurring absence, not of light, not of radiation, but of response. In the region immediately surrounding 3i Atlas, within a spherical range extending approximately 500 kilometers from its core, electromagnetic noise dropped to near zero levels. There were no background pulses, no thermal spikes, no particle scatter. The space around it was quiet. Too quiet. This void came to be known as the silent zone. And by 12:03 Universal Time, it had persisted for over 13 full minutes. In interplanetary space, silence is relative. The solar system hums with background radiation, fluctuating solar wind, particle collisions, and electromagnetic chirps from countless sources. Even empty zones echo slightly with residual charge, thermal currents, and cosmic noise. These are the baselines against which all sensors are calibrated. But the sensors were showing something else. Within this silent zone, radio waves failed to reflect. Infrared scatter declined to statistical noise. Even high-energy particle sensors detected a measurable dip in collision rates. Instruments stationed at the Earth Lagrange 1 point reported that signals passing through this region lost amplitude. Lasers aimed at the object's vicinity encountered diffraction anomalies. It was not that the object was blocking signals. The space around it was absorbing them. The boundary of the silent zone was spherical and stable. It moved with the object, not ahead of it, not behind it, encasing it. The shell did not fluctuate or respond to external input. It held at a constant radius, as if it had been defined not by mass or field strength, but by instruction. By 12:11 Universal Time, Mars-based radar arrays attempted to probe the zone with frequency sweeps. The signals did not bounce back. Instead, they decayed, not absorbed by dust or gas but flattened, as if entering a region of altered physical behavior. No thermal bloom was recorded, no emission spike, just quiet. Only two known natural phenomena can create such behavior. The first is a plasma sheath, which occurs around high-speed bodies during atmospheric entry. In these cases, charged particles form a shield that blocks radio signals. But 3i Atlas was not entering an atmosphere, and the silent zone was too cold, too uniform, too symmetrical. The second is a field cancellation envelope, a phenomenon created in lab environments when standing waveforms are used to cancel external frequencies. This requires precise energy input, spatial control, and active modulation. It requires design. Further analysis revealed something deeper. Inside the silent zone, light delay was measurable. Observers tracking starlight that passed behind the object recorded a microsecond lag, consistent with path bending. This was not gravitational lensing. The mass of 3i Atlas is far too low for such an effect. It was refractive delay. Something in the silent zone was shifting light. This suggested a structured medium, invisible, transparent, but active. A boundary not of mass but of phase. Light passed through, but it hesitated, as if slowed by a membrane not seen but present. The persistence of this zone defied natural expectations. Radiation should fluctuate, fields should decay, noise should return. But none of those things happened. Even after the jets pulsed, even after surface shedding, even after orbital drift, the silent zone held its shape. No feedback loop was detected, no decay gradient. The silence was total, sustained, unbroken. And when space falls this quiet, when physics loses its usual signatures, something else is at work. Not chaos, not accident, but structure. In astrophysics, a void is rarely empty. Sometimes, silence is just the name we give to whatever refuses to speak in our direction, and sometimes it is the clearest signal of all. At 12:16 universal time, during a focused photometric sweep of 3I Atlas's core body, researchers made a discovery that disrupted the assumptions about how the object interacts with light. When solar photons struck the surface, a measurable fraction of them vanished, not reflected, not scattered, not re-emitted, but absorbed without corresponding thermal output. In other words, incoming light was being taken in, but not turned into heat or light. This became known as the photon absorption discrepancy. The surface of the object had already been categorized as dark, based on albedo readings showing less than 3% reflectivity. That was unusual, but not unheard of. Many interstellar bodies are carbon-rich and absorbent. However, when heat maps were aligned with light absorption data, something was missing. For the amount of light the object was absorbing, its surface should have been significantly hotter. But it was not. High-resolution thermal scans showed a near-constant temperature plateau across the object's skin, just above 170 Kelvin. That's well below expected values for an object at its solar distance receiving direct light. In a natural body, more photon absorption equals more surface heating. Here, the numbers did not match. The light was going in, but the heat was not coming out. This raised one possibility, that the energy was being stored. In artificial systems, energy storage often takes the form of capacitive buffering, light converted into electrical or vibrational energy for later use. Some theorists propose that the object may contain subsurface layers with energy-absorbing properties. These materials would convert photon energy into other forms, mechanical tension, chemical states, or even directional flow, without emitting the usual thermal signature. The object was not glowing, it was withholding. To further analyze this, a team from the Infrared Geometry Array ran spectral balance comparisons across the visible and near-infrared bands. They expected to find consistent blackbody radiation curves matching the light intake. Instead, they found dips, specific frequency bands where light was being absorbed but not re-emitted. These dips were not random, they were narrow and precise, exactly the kind of signature you would expect from a filter, one tuned to specific wavelengths. The absorption pattern resembled that of engineered photonic surfaces, which can selectively trap or reflect desired frequencies while transmitting others. These are used in advanced solar sails, energy harvesting systems, and optical cloaks. Natural bodies do not exhibit such filtration profiles. And then came a second discovery. The discrepancy was angle-dependent. As the object moved through space and its solar angle shifted, the depth of absorption in certain bands increased. This meant the surface was not absorbing uniformly. It behaved like a directional collector, tuned not just to take in energy, but to prefer it from one vector. This is function, not form. Even more remarkable was the finding that some of the absorbed light reappeared later, not at the surface, but in the exhaust of the jets. A tiny fraction of photon energy absorbed hours earlier seemed to re-emerge as high-energy plasma emissions during synchronized jet events. The timing correlated closely with storage hypotheses: light absorbed, delayed, then discharged. That is not comet behavior. It is conversion. It is the transformation of solar input into calibrated output. And it suggests that 3I Atlas is not just reacting to sunlight. It is harvesting it, not for heat, but for something else, something controlled. Because in nature, light feeds warmth. But in systems built for precision, light feeds purpose. At 12:34 universal time, orbital tracking data from 3 separate monitoring arrays confirmed what had long been suspected but never directly proven. Despite active jet emissions and continuous orbital adjustments, the internal axis of 3I Atlas had not shifted. The object maintained the exact same inertial orientation in space, without precession, without wobble, and without any measurable torque-induced drift. It was holding a stable axis under thrust. This in itself contradicts nearly every known principle of natural object propulsion. When a comet or asteroid emits gas or ejecta from any point on its surface, Newton's third law applies. The reactive force of that emission imparts angular momentum to the body, typically causing it to spin or tumble. Most cometary jets, even when weak, introduce rotational instability. Bodies in space are rarely balanced enough to emit mass without some level of orientation change. But 3I Atlas did not spin. It did not tumble. Its axis remained fixed. This axis, aligned to within less than 1 degree of solar north, persisted across all observational baselines. Radar arrays tracked surface features for rotational drift and found none. Doppler spectroscopy from the Lagrange relay system revealed no lateral movement in surface-bound mass indicators, and long-range telemetry from the ESA optical beacon array confirmed no tilt change over a full 6-hour interval, yet the object was accelerating. Jet emissions were consistent, timed, and powerful. The estimated delta V was sufficient to shift orbital trajectory by measurable degrees, and still the axis held. Not even a minor precession cycle was detected. That means the thrust was being balanced, not just in force, but in torque vector, and that requires control. The only known way to maintain a fixed axis while applying a symmetric thrust is to compensate in real time, either by varying the thrust magnitude across multiple jets, or by dynamically adjusting the angle of emission. Both require active response. This is not possible for passive cometary jets. Natural jets erupt when heated, without regard for symmetry or direction. They do not calibrate, they do not compensate, and they do not hold an axis under emission. Further evidence emerged in the long-exposure visual analysis from the Martian Orbital Observer. The plumes of emission trace 3 perfect vectors, each angled to counterbalance the other. Like the legs of a tripod in vacuum, each jet produced exactly the thrust needed to maintain position without rotation. The internal system holding that balance, if one exists, would need to be capable of reading the object's position, velocity, and angular momentum in real time. It would also need to modulate outputs down to the millisecond. That is the definition of an attitude control system. Satellites use gyroscopes, spacecraft use star trackers. But what about interstellar objects? 3I Atlas was discovered entering the solar system with a unique trajectory, and it has continued to defy expectations since. This latest evidence adds to the growing list. A body that holds a stable axis under propulsion is not a drifting rock. It is a craft, or something that behaves like one. One final observation sealed the analysis. At 12:51 universal time, a solar wind fluctuation struck the object, a minor coronal stream detected by heliospheric monitors. Most comets would respond with visible surface stress or emission spike. 3I Atlas adjusted its thrust vectors instead. The jets subtly curved, micro-correcting their angles without breaking synchronization. The axis remained motionless, not just fixed, protected. In deep space, the only way to remain still while moving is to balance forces with precision, and precision is never an accident, it is engineered. At 12:58 universal time, the solar particle chemistry array aboard the Mars-facing relay satellite initiated a pass-through spectral analysis of the exhaust plume surrounding 3I Atlas. Its objective was to break down the molecular composition of the outgassed material and compare it to known cometary baselines. Within 42 seconds, the system flagged an anomaly, one that had never been recorded from any natural solar system object. The hydroxyl ratio was inverted. In standard comet outgassing, solar radiation splits water molecules into hydrogen and hydroxyl ions. The resulting plume always skews heavily toward free hydrogen, which is lighter and travels further, while the denser hydroxyl trails closer to the nucleus. This distribution forms a known pattern, one that has been catalogued in dozens of solar comets. But 3I Atlas did the opposite. Hydroxyl ions dominated the forward region of the plume, while free hydrogen was suppressed, lagging in smaller quantities and staying closer to the jet origin points. This inversion was immediate, persistent, and uniform across all 3 jet vectors. Such a pattern contradicts natural photodissociation behavior. To verify, scientists ran the detection through multiple crossband conformations, ultraviolet line scans, mass spectrometry, and Doppler drift curves. All returned the same ratio. The hydroxyl count was too high, the hydrogen too low. This suggested one of 2 things. Either water was not the primary molecule being broken down, or the breakdown was being manipulated. The first possibility required exotic chemistry. Substituting standard H2O for an engineered compound such as hydroxyl-rich hydrates or oxygen-bonded nanofluids could produce an inversion, but no such natural material has ever been found in deep space with that profile. Even interstellar ices show standard breakdown ratios under solar influence. The second possibility was more controversial: active filtering. Some researchers proposed that the object might be selectively retaining hydrogen, either through electromagnetic trapping or internal recapture, and only releasing hydroxyl-rich byproducts into its exhaust. This would mean the jet emissions were not waste, but filtered outputs, and the hydrogen, the lightest and most energetic part of the reaction, was being held back, stored, possibly used internally. If 3I Atlas had the ability to separate molecular components during ejection, that would imply control over its chemical processes, not just passive outgassing but modular reaction management, the kind used in propulsion systems where energy efficiency is maximized by isolating useful elements and discarding inert ones. In deep space missions, hydrogen is valuable as fuel, as coolant, as a propellant base. Hydroxyl is less so, so the object might be shedding what it does not need and keeping what it does. Further evidence emerged in the form of infrared spectral lags. Each time a jet pulse occurred, the hydroxyl spike led the emission signature by 12 milliseconds. Hydrogen never surged. Its emission curve remained flat. This suggested staged release. Hydroxyl out first, hydrogen retained or delayed. Over 10 full cycles, this behavior repeated identically. The inversion was not random, it was sequenced. By 1317 universal time, deep core analysis models simulated what kind of internal architecture would be required to filter molecular outputs in real time. The answer was precise cavity alignment, adjustable pressure regulators, and surface membranes designed to bond or deflect specific ions. Such architecture does not form in rock, it is built. The inversion is not just a chemical curiosity, it is a marker of intent. Because in thermodynamics, every byproduct tells a story. And when the waste material is what nature usually keeps, and the fuel is what nature usually loses, the script has been rewritten by something that knows how to read it. At 1324, universal time, mission control at the Earth Lagrange 1 tracking station issued a quiet correction to its telemetry baseline. 3I, Atlas had just changed speed, not at perihelion, not under solar pressure, not near a planetary encounter, but mid-orbit. With no gravitational influence nearby and no detectable change in jet output, the object's velocity had increased by nearly 1.6 meters per second. This was not expected. It became known as the mid-orbit acceleration shift. In celestial mechanics, acceleration typically follows clear rules. Gravitational assist from nearby bodies, thermal recoil from solar radiation, or sudden outgassing events all produce measurable and explainable changes in momentum. But 3I Atlas was not near any planet. There was no flare, no impact, no visible emission spike, and yet the shift was real. Within 3 observation windows across 3 monitoring arrays, one from Earth's shadow, one from Martian high orbit, and one from the lunar reflector grid, the same adjustment was recorded. The object's trajectory had steepened. Its orbital arc was tightening, nudging it closer to the inner system at a slightly faster rate. No natural body has ever displayed such an isolated, clean acceleration. The timing was equally strange. It occurred during what should have been the object's most inertial phase, the segment of orbit between Mars's outer influence and solar proximity. No known forces operate strongly there. Most bodies simply coast through this region with predictable drag. But 3I Atlas was not coasting, it was correcting. Researchers combed through thermal and spectral data for evidence of jet activity. While the 3 synchronized jets were still firing on the 6.4-second pulse cycle, there had been no increase in temperature or brightness. no sign that the jets had fired harder. However, when those emissions were studied more closely, a subtle pattern emerged. The angle had changed. By just under half a degree, the thrust vectors had shifted, not dramatically, but enough to redirect the net force slightly in the direction of orbital travel, rather than purely for stabilization. This was an intentional vector bias. Instead of maintaining its current orbital energy, the object had nudged itself forward. And that shift had consequences. Simulations run by the Planetary Orbital Mechanics Lab showed that a 1.6 meter per second velocity gain at this orbital point would shorten its solar loop by over 900 kilometers. That would place 3I Atlas closer to the inner heliosphere on its next pass, increasing radiation exposure, gravitational stress, and solar wind interaction. In natural terms, this is the opposite of what most bodies do. Objects entering solar systems usually lose energy. They slow, spiral, and scatter under drag forces. But this one was diving deeper, by choice. Further analysis showed something even more unusual. The acceleration shift followed a brief pause in surface shedding. For nearly 12 minutes prior to the speed gain, the surface had gone completely quiet. No fragments released, no flickering emissions. This silence, then acceleration, suggested preparation. Some hypothesized a storage mechanism, building up force, timing the release. Others believed it was navigational, because if the object had entered a new orbital subphase, where microcorrections are made to align for a future encounter, planetary, solar or otherwise, then the mid-orbit acceleration was not propulsion. It was positioning, and positioning means foresight. In deep space navigation, the ability to adjust mid-arc without external force is a sign of intent, especially when it is done with mathematical precision. Because in orbital mechanics, drifting is easy. Choosing your path, that takes awareness. At 1341 Universal Time, shortly after the mid-orbit acceleration shift had been confirmed, a separate signal caught the attention of the magneto-optical imaging team. It was faint, delayed, and oddly positioned. While the primary jets of 3I Atlas had been well documented, 3 synchronized pulsed plasma emissions directed for stability and minor propulsion, this signal came from somewhere else. It was not from the main axis, it was lateral, and it was moving. This new observation came to be known as the emergence of secondary emission vectors. Initially dismissed as thermal noise, the pattern repeated itself across 3 different spectral arrays. Low-level bursts of charged particles were escaping the object from angles not aligned with the primary jet axis. They appeared in bursts, short-lived and inconsistent in power, but geometrically precise. These were not random leaks or natural venting events. They followed arc patterns, and they obeyed angular symmetry. At first, the emissions were spotted at 34 degrees above the equatorial plane, a strange angle for spontaneous outgassing, but well within the operating envelope of a designed thrust port. 5 minutes later, a second emission emerged at the opposite side, mirroring the angle but reversed in spin direction. This bilateral symmetry hinted at design, not erosion. But what truly confirmed their importance was the timing. Each secondary burst occurred exactly 4.8 seconds after a full cycle of the main trijet pulse. Not before, not during, always after. It was as if the object exhaled first, stabilized its position, and then adjusted. These secondary vectors appeared to play a fine-tuning role. Instead of major propulsion, they produced gentle nudges, detectable only because the background vacuum of space allowed even small force signatures to be traced over time. Their strength was measured in millinewtons. But their effect, over thousands of kilometers, was measurable. They altered the micropath. Most striking was their orientation, not directly backward, not perpendicular to motion, but curved, almost spiral-shaped. The emission trails formed arcs that wrapped around the object's main vector like ribbons of ionized vapor. These emissions appeared to modulate based on external conditions: solar wind, magnetic flux, and inertial drift. In other words, they reacted to the environment. No natural process does this with such precision. When comets shed gas or ice, the direction is governed by temperature gradients, surface composition, and solar proximity. The result is chaotic. Jets sputter, redirect, and often cause spin or tumble. But here, the secondary emissions did not destabilize the object. They corrected it. Like micro-adjustments in spacecraft thrusters used to keep satellites in exact orbit. more data confirmed the behaviour. By 1357 Universal Time, the emission showed signs of vector blending when a secondary jet fired while the object rotated slightly along a single axis. The emission strength adapted accordingly. Stronger at the start, tapering as alignment was restored. That is feedback control, that is closed-loop guidance, and that is not cometry. Researchers began simulating what kind of control system could produce such emissions. The model pointed to a layered system: primary thrust for bulk movement, secondary jets for angular adjustments, and a timing system that linked them both via synchronized pulses. This is consistent with advanced navigational logic, not just maintaining orientation, but adapting it based on prediction. Prediction is key, because these secondary vectors did not simply respond to instability, they anticipated it. In multiple cases, the jets fired before any measurable drift was visible. The object was adjusting for something it already knew was coming: a plasma wave, a flux shift, or a microgravity deviation. That is the behavior of craft, not debris. When something releases energy, it leaves a trail. When something uses energy to steer before it needs to, it leaves a message. And 3i Atlas, with every one of its secondary emission vectors, was writing in motion and speaking in trajectory. At 1409 Universal Time, during a composite surface reconstruction effort using synchronized imaging from 3 orbital platforms, analysts noticed a subtle but persistent contradiction in the physical shape of 3i Atlas. The surface geometry, already known to be irregular, revealed angles and contours that did not align with the thermodynamic expectations of an object heated by the sun and venting material through jets. The object's form appeared to ignore heat flow. This chapter came to be known as geometry beyond thermodynamics. Under natural circumstances, when an object is subjected to intense thermal energy from a single directional source, such as the sun, the process of sublimation, erosion, and phase change sculpts the body over time. Peaks erode, cavities deepen, soft materials expand. The result is a predictable thermodynamic profile, smooth on the sunward side, pitted and outcast toward space. But 3i Atlas did not follow this pattern. Instead, its sun-facing side displayed a sharp array of faceted surfaces, angled like armour, with reflective channels built into their contours. These features acted more like energy guides than erosion marks. In fact, the surfaces facing direct sunlight were flatter, denser, and more regular than those hidden in shadow. This was not the result of chaotic heating. It resembled architecture. Further anomaly emerged in the thermal gradients themselves. Using infrared elevation mapping, researchers overlaid temperature data on top of the object's geometric structure. In natural bodies, heat diffuses gradually from illuminated to shadowed zones. On 3i Atlas, heat lines bent unnaturally, following ridges and valleys that aligned with its structural planes, not the direction of incoming radiation. The object was guiding heat, or redirecting it. One theory proposed that the internal structure of the body contains phase-change materials, or heat sinks that pull energy laterally rather than allow it to accumulate on the surface. But this still doesn't explain the external angles, the smooth, mirror-like facets that rise and fall in synchronized patterns across multiple quadrants of the object. Another possibility, the surface is designed to scatter or trap specific wavelengths of energy, using geometry to influence radiation behavior. This is a technique used in metamaterials, human-engineered surfaces that can control light beyond traditional reflection or absorption. And while no such material has ever been found naturally, the shapes on 3i Atlas matched several known patterns of photonic deflection. One surface array, identified on the object's northern hemisphere, showed a tessellation of triangular units, each precisely 38 degrees in offset from its neighbour. When light struck this array, it diffracted in a specific spiral pattern that suppressed infrared output and prevented localized heating. This is not random geometry. It is active thermal control, and that has consequences, because if the object is shaping heat, not just surviving it, but sculpting its flow, then its form is not the result of passive endurance. It is deliberate, functional, a response not to nature, but to need. Moreover, these same geometric features did not erode over time. From the first full-scan imaging conducted in early October to the current readings from November 16th, the ridgelines and surface angles remained identical. No melting, no collapse, no cratering. The object is withstanding both radiation and internal pressure without changing shape. That alone is nearly impossible for any natural body under active jet propulsion and solar heating. It raises a fundamental question. What kind of material, and what kind of design, retains perfect form under thermal stress? The answer may lie in a simple truth. When a shape does not follow erosion, and when heat does not dictate structure, the object is no longer defined by what surrounds it. It is defined by what it was built to do, and whatever 3i Atlas was built for, it is doing it, without compromise and without decay.